Okay, hello everyone. My name is Hongchang Zhou, and I'm a PhD student from the University of Tokyo. Welcome to my presentation. Today, my topic is a multiscale model for predicting fatigue strength of the bainitic steel, considering grain boundary effects by a generalized evaluation method. Okay, here's the outline. Firstly, I would like to introduce the research motivation, and then I will show some detailed information about our multiscale modeling strategy. And here are three sub-models. First one is the microscale finite elements analysis model. Second model is the microscale material modeling. And the final model is the theoretical model of the crack injection and propagation. And then I will introduce the foundation part of the model. Finally, I would like to summarize our research work. Okay. We know that the microstructure will have influence on the fatigue life, and the steel with the finer grain will show a longer fatigue life and a higher yield strength and higher fatigue limits. However, there has not been an effective model to quantitatively explain the influence of the microstructure on fatigue life. And recently, we proposed a multiscale model to predict the fatigue strength of the ferrite steel. We know the ferrite and pearlite steel is the most widely used as a structural steel, and it has the simple microstructures which can be characterized by the ferrite grain size and pearlite band thickness. So in our previous model, we made an ellipse observation for simulating the shape of the ferrite grain and pearlite colloids, and we generated the grain distribution on the surface plane and the inside plane. So finally, we can predict the fatigue life and the limits, which can get a good agreement with the experiment results. However, our previous model cannot be applied to the bainite steel directly. We know this is a very high-grade steel because it has much more complicated geometrical features, and the grain orientations and the misorientations can be different from those of the low-grade steel. So our research modification is to develop a more general method to characterize the microstructure features on fatigue strength, which can be applied to high-grade steel. Okay, I would like to introduce our modeling concept. Firstly, we know it's not easy to define the crack initiation length. From our experiment observation, we focus on the crack initial sites, right here. We can find the small crack when the cycle number is 2000. However, the total fatigue life is more than 200 cycles. So that means a crack can be observed for less than 1% of the fatigue life, and that means the crack growth life is more than 99%. So in our model, the total fatigue life is estimated only from the crack growth life. And also, we simplify the complicated 3D fatigue phenomenon to the 2D problem with two steps. The first step, we consider the crack initial site is on the surface plane. And step two, we calculate the total fatigue life by assuming crack growth in the inside plane. And we consider that the effect of the grain boundaries is characterized by the distance between grain boundary and the misorientation between adjacent grains. And our multiscale modeling strategy integrates the multiple model with large-scale difference, right? Okay, here is the outline of our proposed model. The input data includes the test conditions, the tensor property steel, and the microstructure informations. And we have three sub-models here: the macro finite elements analysis, and the microstructure, and the crack growth. Finally, we can obtain the fatigue life and limits. Firstly, I would like to introduce the sub-model one. The target of this model is to calculate the relative elastico-plastic strain tensor and define the active zone. We define the cyclic stress-strain relationship by using the empirical formula by this equation. The input dates are only the monotonic tensor property, and then we define the active zone as the surface domain, which is large enough to contain a possible crack initial site. And then the microstructure. Okay, the required date of the microstructure information I show here we perform the EBSD analysis and we use the OIM software to fit the grain at the ellipse. So we can get the major and minor axis length and the major axis angle. And also from the EBSD results, we can get the orientation of each grain. And we measure the distance between the grain boundary by using the segment length. And for fair and pearlite steel, the information of the fallen fraction of the pearlite phase and the pearlite band thickness is also needed. So with this information, we generate the spatial grain distribution in the surface plane. The active zone is the surface plane where a crack is possible initiate, and the surface element is the simplification of the respective grain location. So all the grain are assumed as a possible crack initial site in our model. And then we generate the spatial grain distribution in the inside plane. We assume the initial grain shape as the semi-ellipse, and the ferrites on the pearlite colloids are assumed as a rectangle and a square. So we assign this grain to the grain line. The grain line is calculated based on the crack shape transition. And then we can get the grain distribution like this. And also we assign the grain orientation for the adjacent grain by the disorientation from the EBSD results. Okay, I will introduce the model of crack growth. The basic theory is the interaction theory between the crack and the grain boundary. This is originally proposed by Professor Tanaka and later modified by Professor Shibanuma by assigning the physical meaning of the parameters. Here A is the crack length and C is the slip band length, and the relationship between A and C can be expressed by this equation. And finally, we calculate the crack growth law by using this formula. The delta CTSD means the crack tip sliding displacement range, which can be calculated by using this formula. And in this theory, the input data includes the applied stress range, and grain size, and the friction strength to move to location, and the crack length. And we can get many output data, including vertical life. Okay, in this theory, the crack growth resistant force is the friction strength to move this location, which is also the yield shield strength in single crystal expressed by the Hall patch law. And we consider the cyclical softening and hardening behavior by using the ratio between the cyclical yield strength and the monotonic yield strength. So finally, we can calculate the friction strength to move this location for the respective phases. And the crack growth driving force in this theory is the effective shear stress range on each grain. We consider the effect of the crack shape transition and the strain distribution, and also the crack opening closure effect considered. And then the delta tau can be finally calculated by using this formula, considering the slip band system of a BCC crystal. And this slide shows the evaluation of vertical life. We consider the crack initial at every grain assigned on the surface element, and then we calculate delta tau for all the compilation of the adjacent grains. The interaction theory between the crack and the grain boundaries was applied. So finally, the vertical life of the specimen can be determined by the minimum number of cycles to value at all the crack initial sites. And then I will introduce the foundation part of the model. We use the two kinds of ferrite and pearlite steel and one bainite steel. And here, this table shows the mechanical and microstructure property of the test steel. We can see the grain size show large difference for each steel. And this three figures shows the microstructure distribution. Okay, and this figure shows the configuration of the specimen. And this is the setup of our 3-point bending test. And we obtain the SN curve from the experiment. And we identify the constant in the classical slope by using steer A, and these two results are our prediction results. So we can find the proposed strategy reproduce the difference between the respective steers successfully, even though their microstructure and the material properties show a large difference. And also the error of the fatigue limits were within only 5% for all the steer. So finally, I would like to summarize our research work. We proposed a multiscale model for predicting the fatigue strength of the bainitic steer, considering grain boundary effects by a generalized evaluation method. So our multiscale model involved 3 submodels. The very important point is that the total fatigue life was evaluated by the crack growth life alone, and our model of the microstructure have been developed effectively considering the distance between grain boundary and the misorientation between the adjacent grains. And we validated our model by experiments using 2 ferrites per steer and 1 bainite steer. The fatigue life and limits was successfully predicted, and the result indicates our multiscale model can predict the fatigue life and limits of steer with microstructures from the coarse ferrite to the fine bainite steer. And our achievement has already published in the International Journal of Fatigue, and it is open access. Okay, thank you for your attention.
Are there any questions? Yes, please.
In your crack propagation life, you mentioned that, well, you usually disregard crack initiation as the crack is very small, 1% corresponded to 1% of the life, that photos of the microstructure that you showed. Okay, but what size of crack you considered to crack initiation?
Okay, thank you for your question. Actually, you can see our specimen with a very thin thickness, only 1.9 millimeter. So our model only consider maybe you can say it's a short crack.
Okay.
But our recently research work, we also validated our model to a long crack. We performed the specimen with the 6 millimeter, and our model also can successfully predict the fatigue life and limits. Yeah, but at present in this presentation, I only show the small specimen. Okay, thank you.
I see. Just you see how do you see that? Because, well, the stress intensity factor is derived based on elasticity, isotropic, homogeneous conditions. Okay, but you are inserting the grain boundaries.
Yeah.
Okay, don't you think this somehow lost some connection to these basic assumptions for the linear elastic fracture mechanics approach?
Yeah. Actually, you can see our crack growth model. We calculated the crack growth rate by using delta CTSP. And this equation shows the relationship between the crack and the grain boundary. The L is the grain boundary. And also we consider the delta tau. This is the driving force. So we consider the applied stress to calculate delta tau. So there's a very complicated process to calculate this parameter. Yeah. If you are interested, I will introduce a very detailed information of how to calculate this value. Actually, this is a very important point in our paper, how to consider this value. Okay, thank you.
Thank you.
I think you have a question.
Yes, so of course the one of the key inputs is the distance between the grain boundaries.
Yeah.
It's okay.
You showed that you just used the intersect method in the horizontal and vertical direction, right? And this particular example you showed of this grain under 45 degrees. So I would guess that, like, why don't you use the actual distance between these two? Like, just for that particular case, for instance, the distance between the grain boundaries on the 45 degrees would be significantly lower, right?
Okay,
The square root of 2. I would guess that that's quite a big impact.
Okay, thank you for your question. I would like to introduce the microstructure model. You see, this is also a very important point in our paper, that we measure the distance between the grain boundary. As I showed before, the grain boundary distance is a very important parameter to calculate that CTSP. So we measure this distance directly from the EBSD result. I mean, in our previous research, we just simplified the grain at the shape of the ellipse. But for the bainitic scale, the grain size and grain shape have a very complicated shape. You can see it's just the shape of the ellipse. So the assumption of the ellipse is not validated for this kind of complicated microstructure. So we just measure directly the grain boundary distance, which means if the distance is smaller, the resistance force for this kind of material is stronger to stop the crack growth. So we use this approach to consider the grain boundary effect.
Yeah, that's exactly the point. So you measure actually the distance in horizontal and vertical direction, but
Yeah,
is it the relevant distance in this for this particular grain on the 45 degrees?
Yes, actually, when the crack can be propagated in this direction or also this direction, or any direction is possible. But considering the distribution of the crack of the grain boundary length, we can measure it from any direction. But finally, we can get a similar this kind of distribution of the grain boundary length, because our EBSD map is a very large size. If you measure it from the horizon direction or the vertical direction, the segment length, the distribution should be the same.
Well, okay. I wouldn't expect that with a texture material, but okay.
Yeah.
Maybe for the materials you studied, that's the case. Okay.
Yeah, thank you.
Nice
very
work,
much.
but
Okay.
Fun?
thank you.
Okay. Any other questions? Thank you very much again.
Okay.